You are sitting inside something that shouldn't exist. Not above it, not beside it, but directly in the center of a million-degree hollow carved out of the galaxy. It surrounds your home like an invisible shell, stretching for hundreds of light years in every direction. And the strangest part is this: we only confirmed it a few years ago. For decades, the soft X-ray glow in the sky confused every telescope pointed toward it. Some astronomers blamed the sun. Others thought their detectors were malfunctioning. No one expected the answer to be so enormous, so elegant, or so quietly unsettling. The solar system is floating inside a cavity that was sculpted by at least 15 massive stars exploding one after another. Their shock waves expanded, overlapped, cleared away the interstellar gas, and heated the remaining traces to temperatures hotter than the surfaces of many stars. Today, that cavity is the space you live in. A hollow 1,000 light years wide, a chamber of thin, million-degree plasma, a scar left behind by giants that died before humans existed. You don't feel the heat. You don't see the light. Yet you are suspended inside the echo of those ancient deaths every moment of your life. And that is the first strange truth. This bubble is real, enormous, and still expanding. But we barely noticed it until modern instruments forced us to look again. When NASA launched a small rocket experiment to measure the mysterious X-ray glow with fresh precision, the result was clear. Only part of the radiation came from the sun's wind. The rest, the majority, was coming from a vast, hot, low-density cavity enveloping everything you know. A structure hiding in plain sight. A structure you have been breathing under for your entire life without having the slightest idea it was there. But the bigger surprise came after. When astronomers mapped the positions of young stars around this bubble, they found something astonishing. The stars were not scattered randomly. They traced the bubble's surface like lights outlining a lantern. A whole generation of stars had been born along its outer shell, where the shock waves compressed gas and triggered collapse, death on the inside, birth on the outside. A bubble made not just of destruction, but of creation. And then came the strangest twist of all. Your sun was not born anywhere near this bubble. It wandered into it. Somewhere in the past 5 or 6 million years, your star drifted across the galaxy's spiral arm and slipped directly into the center of this hollow. No other star near it formed inside the bubble either. You are part of a system that simply passed through the right place at the right time, settling into a cavity made by stellar violence, surrounded by newborn stars that were never your siblings. Your home is a visitor inside a structure built by others. Tonight, you are going to explore that structure. You'll learn how scientists first realized the bubble existed, how they traced its boundaries, how they uncovered the supernova chain that carved it, and why this region of the galaxy is filled with interconnected cavities and tunnels shaped by dying suns. You'll see how your star drifted into this hollow, how stars continue forming along its glowing shell, and why Earth, quiet, blue, fragile Earth, remains completely safe inside this vast cosmic chamber. This is not a story about fear. It is a story about perspective, about the hidden architecture of the Milky Way, about the discovery that space is not empty at all, but patterned, sculpted, and layered. It is the story of the strange thing hiding beyond your solar system, a structure you have lived inside your entire life without ever seeing it. So take a slow breath. Let the noise of the day slide away. You are drifting inside a mystery carved by light and time. And the deeper you go into this hollow, the more you will understand how extraordinary your place in the galaxy truly is. You first hear about the bubble as a grand, almost mythical structure. But its discovery didn't begin with anything grand at all. It began with a quiet confusion in the 1970s, when astronomers noticed something in the sky that shouldn't have been there. No matter where they pointed their instruments, a soft X-ray glow washed across the entire dome of space. It wasn't bright, but it was persistent. It was everywhere, like a whisper of heat coming from all directions at once, and no one knew why. The early explanations were modest. Some scientists suggested it came from the solar wind, brushing against neutral atoms drifting through the solar system. Others suspected noise from the detectors. A few wondered whether the glow might simply be a foreground contamination, an illusion created by the equipment rather than a feature of the cosmos. It was easier to assume the instruments were misbehaving than to imagine something massive and hot lurking beyond the planets. But the numbers refused to cooperate. The intensity of the X-rays was too high for the sun to explain, too broad to be local, too steady to be a mere artifact. The glow didn't fade when Earth moved. It didn't shift with the seasons. It didn't act like anything produced by our star. It behaved like a distant source, but one strangely close at the same time. For decades, astronomers were left with a puzzle that felt like a riddle from the dark. Then, in 2014, NASA launched the DXL mission, a sounding rocket experiment designed to finally separate local X-rays from those arriving from beyond. It was a small mission, quick and precise, and when the results came back, they redrew the map of our cosmic neighborhood in a single stroke. Only about 40% of the detected X-rays came from within the solar system. The remaining 60% came from something much larger, hot interstellar plasma stretching hundreds of light years across. The bubble was real, and the solar system was inside it. That single confirmation changed everything. It meant the space around you is not empty. It is not cold. It is not quiet in any physical sense. Instead, you are surrounded by a heated cavity, a hollow of million-degree gas, thin enough to pass through your body without you ever noticing. You live in a region shaped by events so energetic that they cleared out entire swaths of the interstellar medium. And this leads to the real question. If this bubble exists, if it glows with the X-ray signature of extreme heat, then something must have ignited it. Something powerful enough to carve a cavity nearly 1,000 light years wide. Something strong enough to strip away gas, raise temperatures to 1,000,000 degrees, and leave a fingerprint across the entire sky. To understand the bubble, you need to understand the explosions that carved it. To understand the hollow around you, you have to travel back through millions of years of cosmic history. Back to a time when this region of the galaxy was crowded with giants. Not gentle stars like the sun, but massive ones, heavy enough to collapse under their own weight. Stars that lived fast, burned hot, and died violently. Their deaths are the reason the bubble exists at all, and the evidence of those deaths has been falling onto Earth for millions of years. The story begins with iron-60, a radioactive isotope you won't find naturally on Earth. It does not form in volcanoes, or lightning strikes, or the deep mantle. It forms only in the core of a massive star, and it is scattered into space only when that star dies in a supernova. When scientists discovered traces of iron-60 in the deep-sea sediments of the Pacific, Atlantic, and Indian Oceans, they realized something extraordinary. Earth had been dusted by supernova debris, not once, but multiple times. Iron-60 decays into cobalt-60 and then into nickel-60 at a predictable rate. By measuring the ratios of these isotopes in different layers of seafloor crust, scientists were able to date when the dust arrived. The results revealed two major spikes, one between 3.2 and 1.7 million years ago, another between 6.5 and 8.7 million years ago. Each spike was too broad and too rich in iron-60 to be the result of a single supernova. It meant multiple explosions had gone off in sequence, like thunder rolling across the sky, one boom after another. As the data accumulated, all signs pointed to a single source, the Scorpius-Centaurus Association, a vast family of massive stars that once passed near this region of the Milky Way. Over several million years, roughly 15 of those stars died in supernova explosions, not randomly, not scattered, but clustered in time and space, like fireworks erupting from the same launching ground. Imagine each explosion sending out a shockwave, expanding like a sphere of compressed gas. Now imagine those spheres overlapping, combining, hollowing out the interstellar medium. Each one added heat. Each one pushed matter outward. Each one carved the cavity deeper, sweeping away clouds, dust, and neutral gas. The overlapping shock waves created an enormous empty chamber, a pocket of thin, hot plasma that would eventually become the local hot bubble. And it didn't stop there. The debris from these explosions is still arriving. A slow rain of dust from dead stars, drifting through space until it finds Earth's gravity well and settles into the ocean crust. Every grain of iron-60 on our planet is a time capsule, a message from a star that ended its life in a light brighter than 10 billion suns. The bubble that surrounds you today is not static. It is still expanding, moving outward at around 6 kilometers per second. It carries the memory of each explosion within it. 15 separate deaths woven into a single hollow. This is the origin story of your cosmic neighborhood. You live in a cavity that was once the roaring fire of dying suns. But the bubble didn't only clear space. It changed the future. It sculpted gravity. It triggered creation. And along its surface, the next generation of stars began to form. When astronomers finally mapped the bubble with precision, they noticed something even stranger than the cavity itself. The walls weren't empty. They were glowing with youth, thanks to the Gaia mission, a spacecraft that created the most accurate 3D map of stellar positions and motions ever assembled. We can now see the structure of the stars around you as if someone peeled away the dust and let the galaxy breathe in open air. And when scientists plotted the locations of young stars within about 500 light years, a pattern emerged that no one expected. The youngest stars didn't scatter randomly across the sky. They sat on a curved surface, tracing the outline of the very bubble sculpted by ancient supernova. Imagine an invisible sphere surrounding you, its skin sprinkled with stars like beads glowing on a dark necklace. These stars are not millions of years old like the sun. Many are only a few million years old, barely out of their cosmic infancy. And yet they all share the same home, the outer shell of the local hot bubble. The physics behind this pattern is both simple and beautiful. When the bubble began expanding, the shock waves pushed interstellar gas outward, compressing it along the edges. And when gas is compressed, it collapses. When it collapses, it heats. And when it heats enough, it ignites into new stars. The chaos of dying suns became the engine for a new generation of life. The destruction in the center created the pressure needed to sculpt stars along the rim. It's a kind of cosmic recycling that feels almost intentional, as if the galaxy itself were practicing a quiet form of order. As scientists looked more carefully, they identified 4 major waves of star formation that followed the bubble's expansion. First came Upper Centaurus Lupus, then Lower Centaurus Crux, then Upper Scorpius. Later, farther along the rim, even younger stars appeared in Taurus, Lupus, and Ophiuchus. Each region marked another step in the bubble's growth, like rings in a tree trunk recording its age. As the cavity expanded, new stars lit up along its boundary. The bubble didn't just record the past, it was actively shaping the present. The realization changed how astronomers see the galaxy. This hollow around you isn't just a remnant, it's a nursery, a structure capable of triggering birth long after the deaths that created it. A place where the imprint of ancient explosions still guides the formation of young suns. Every bright star you notice in those regions may be living on the bubble's skin, glowing because the galaxy turned violence into creation. And yet your sun is different. The young stars around you were born from the bubble's outer shell. But your own star carries no such connection. It didn't emerge from the bubble's pressure. It wasn't shaped by the supernova winds. It arrived much later, drifting in from elsewhere, like a traveler who wandered into a room whose story had already been written. But what about our own star? Where does the sun fit in this story? The young stars outlining the bubble fit the pattern perfectly. They were shaped by its pressure, born along its curved outer edge, illuminated by the same chain of supernova that carved the cavity. But your sun breaks the pattern entirely. It wasn't born inside the bubble. It wandered into it long after the fireworks ended. Your star orbits the center of the Milky Way once every 225 to 250 million years. Along the way, it moves through different regions of the interstellar medium. Dense clouds, thin stretches, pockets of dust, and sometimes, as it turns out, a giant cavity made by dying suns. When the first supernovae erupted in the Scorpius-Centaurus Association, the sun was nowhere near this region. It sat almost 1,000 light-years away, far outside the zone affected by the expanding shock waves. But the bubble didn't stay put. Over millions of years, the overlapping supernova shells pushed outward, hollowing out a space that grew wider and wider. Meanwhile, the sun continued drifting along its orbit, crossing new neighborhoods of the galaxy the way a ship crosses different currents in a vast sea. Eventually, the paths of the sun and the bubble intersected. About 5 million years ago, the edges of the bubble expanded into the region the sun happened to be moving through. Slowly, steadily, Without any drama or visible sign, the solar system slipped inside the cavity. It didn't arrive with the other stars along the rim. It arrived late, like someone walking into a hall long after the music ended and the crowd dispersed. Today, the sun sits near the center of the local hot bubble, not because it belongs there, but because the galaxy arranged a quiet coincidence of motion and timing. You live inside a structure built by stars that died long before your own star approached the scene. It is a reminder that the galaxy's stories have been unfolding for millions of years before you arrived, and they will continue long after you drift into the next region of space. So, if we're now sitting near the center of this million-degree bubble, why do we feel nothing at all? What does it mean to live inside a million-degree bubble and not notice? On paper, that number sounds terrifying. 1,000,000 degrees sounds like it should melt worlds and strip atmospheres, not cradle a quiet blue planet where you can sit back at the end of the day. And yet here you are, in the middle of a cavity measured at about 1,000,000 degrees, completely unaware. No burning sky, no searing wind, just calm. The key to this paradox lies in the difference between temperature and density. Temperature tells you how much energy each particle carries. Density tells you how many particles there are. Inside the local hot bubble, each atom is racing around with a lot of energy, but there are very few atoms to begin with. The gas is so thin that even though the particles move very fast, there just aren't enough of them to affect you. The total energy is low, spread across a space hundreds of light years wide. Picture a few sparks drifting through a stadium. If you picked up one of those sparks, it would be hot. But if you sit in the stands, the air still feels cool. Inside the bubble, the plasma is hot in the same way. Individual particles carry a lot of energy, but the space between them is enormous. Compared to the air in your room, the hydrogen around the solar system is more than 100 times less dense than typical interstellar gas. So yes, you are inside a 1,000,000-degree environment, but it is 1,000,000 degrees in a room almost completely empty. On top of that, you are wrapped in layers of protection. The heliosphere, blown by the sun's wind, helps shield you from charged particles. Earth's magnetic field bends many of the remaining cosmic rays away. The atmosphere soaks up most of the rest before they can reach the ground. High temperature does not always mean danger. Sometimes, it just means a few lonely particles moving very fast in a very empty room. The local hot bubble is not a furnace you are about to fall into. It is more like a faint, ghostly halo of warmth stretched across space by explosions long past, quietly glowing while you live your life far below. And once we mapped the heat around us, we started to see something even stranger. When astronomers were done puzzling over the bubble around you, they did something simple and profound. They stepped back. Instead of looking only at the local hot bubble, they asked a larger question. Is this cavity unique, or is it part of a bigger pattern? When they surveyed more of the sky in X-ray, radio, and hydrogen emission, the answer became hard to ignore. Your bubble is not alone. The Milky Way is full of hollows. Where many supernovae go off in the same region over millions of years, they don't just carve out one neat sphere. They create what astronomers call a superbubble, a vast, overlapping cavity where multiple shock waves have cleared out the gas. Seen from afar, these regions would look like great hollows in the galaxy's disk, each one a record of clustered stellar deaths. The local hot bubble is just one example, tucked inside a network of other cavities, like a room in a much larger building. Some of these neighboring structures are famous in their own right. Loop Y, for example, is a huge superbubble likely powered by supernovae in the Scorpius Centaurus region. The Gum Nebula is another, an enormous, faint shell of gas that may be the faded remnant of old explosions and stellar winds. Radio maps, X-ray surveys, and infrared observations all reveal parts of these cavities, each one stretching across hundreds of light years, sometimes overlapping, sometimes bumping against each other like soap bubbles crowded together in a sink. Between them, there are not just walls, but corridors. Astronomers have found evidence for hot, low-density tunnels linking one superbubble to another. One such pathway, sometimes called the Canis Major Tunnel, appears to connect the local hot bubble to gas associated with the Gum Nebula or a related structure. Another channel may lead toward Centaurus and Loop 1. Along these routes, energy and material can flow, allowing shock waves and hot plasma to travel from one cavity to its neighbors. These superbubbles shape where stars form. Each one has a shell where gas is compressed and cooled, providing the right conditions for clouds to collapse and new stars to ignite. The tunnels between them may even allow disturbances traveling through one region to seed star formation in another, turning the galaxy into a loosely connected web of cause and effect. A supernova in one neighborhood might indirectly help light up stars half a spiral arm away. So when you picture the Milky Way, it helps to let go of the idea of a smooth, uniform disk of stars. Instead, imagine something more like a foamy structure, full of hollows carved by old violence and lined with new light. Cavities, shells, tunnels, and filaments, all layered together. You are sitting inside one of those hollows, linked by invisible corridors to others you will never see. Even destruction has a pattern. Even chaos has a shape. The galaxy you live in is far more structured and far more connected than a simple map of dots on a flat plane can ever show you. And in the middle of all that foamy structure, you are just quietly floating inside one of its hollows. You have just walked through a lot of structure in your mind. Bubbles, tunnels, hollows, and shells. Before you go any farther, let all of that soften. Take a slow breath in and a slower breath out. You are not in a hurry. The galaxy has been reshaping itself for millions of years. It can wait while you rest for a moment inside it. Imagine yourself floating at the center of your bubble, not racing, not falling, just drifting. Around you, the darkness is soft rather than harsh, a deep navy instead of pure black. Far away, curved in a faint arc, lies the shell of young stars along the bubble's skin. Their light is gentle, like pinpricks through a dark curtain. You are inside something ancient, but it is quiet now. The shock waves have passed. The gas has thinned. What remains is warmth too faint for your skin to feel, and a structure too large for your eyes to notice. From your point of view, nothing is happening, yet you are resting in the calm left behind by storms that ended long ago. Think about your day for a moment. The errands, the messages, the deadlines, the brief spikes of tension. Each one was its own small burst of energy. Now you are on the other side of them, in the quiet that follows. Just as the galaxy leaves behind pockets of stillness after it storms, you are allowed to have this pocket of stillness tonight. Out there, stars still explode. New bubbles are being carved. But you do not have to carry any of that. Tonight, you are only here to understand a little, to feel a little wonder, and to rest inside the afterglow of ancient endings. It is calm here now. You are safe, floating inside your own quiet hollow. But what does it really mean for a star to die in a way that can shape bubbles like this? A supernova doesn't begin as an explosion. It begins as a quiet brightening. A star that has lived in steady, patient light for millions of years suddenly starts to glow a little stronger, the way a lantern warms just before you strike the wick. Night after night, it climbs in brightness, as if taking a final deep breath. To ancient sky watchers, these stars appeared from nowhere. Some grew so bright they rivaled the full moon. A few were even visible in broad daylight. But despite everything you've seen in movies, a supernova is not chaos. It's choreography. Inside the star, the core reaches a point where it can no longer hold itself up. For massive stars, that collapse happens in a fraction of a second, triggering a shock wave that rebounds through the layers above. For white dwarfs in a binary, runaway fusion ignites like a flashbulb. In either case, the outer layers of the star are lifted and flung outward at about 10,000 kilometers per second. The core, suddenly stripped bare, becomes a neutron star. Or, if the star was truly enormous, a black hole. From the outside, though, it doesn't look violent. It looks like a bubble of light swelling in slow motion, each moment stretching wider, softer, rounder. Imagine a glowing lantern blooming in the dark, one that grows so large it could swallow entire worlds without anyone near it feeling a thing. As its shell expands, it ionizes the gas around it, sculpting a nebula, a drifting remnant that will eventually seed the next generation of stars. This is the galaxy's quiet rhythm, the end of one life giving shape and material to the next. Every supernova is a heartbeat, a rare pulse in the vast timeline of a galaxy that waits centuries between each one. For a brief moment, a single star can outshine entire galaxies, then fade back into the darkness, leaving a cloud, a whisper of dust, and the building blocks for worlds yet to come. A supernova is the universe's way of recycling, and these lanterns of light, brief, brilliant, and rare, are far more uncommon than they feel when you hear the word supernova. But for all their beauty, how often does the galaxy actually light one of these candles? In a galaxy filled with hundreds of billions of stars, you might expect supernovae to be going off all the time. But the Milky Way is quieter than you think. On average, the galaxy produces only 2 or 3 supernovae per century. 100 years, and only a few stars reach their final flare. Most occur far across the spiral arms, wrapped in veils of dust that hide their brilliance from Earth. If our eyes could see through the dust, the night sky would occasionally host a star that suddenly blossoms, burns bright for weeks, and then slowly fades. But because of that dust, most of these deaths happen unseen. The ones we do know about left deep marks on human history. SN 1006, recorded across several cultures, was so bright it cast shadows at night. Centauri 4 gave rise to the Crab Nebula, its ghostly filaments still expanding today. Later came the supernovae, studied by Tycho Brahe and Johannes Kepler. Each one a reminder that the heavens are not fixed, but alive. Yet the best evidence for supernovae near Earth doesn't come from telescopes. It comes from the ocean floor. In deep-sea sediments, scientists found traces of iron-60, a radioactive isotope forged only in supernovae. It doesn't exist naturally on Earth. More of it turned up in the Indian Ocean, the Pacific, the Atlantic, then on the Moon's surface, untouched by Earth's atmosphere. These atoms settled here after drifting across space. Dating these layers revealed two major spikes in iron-60. One occurred roughly 2 to 3 million years ago. Another between 7 and 8 million years ago. Each spike is too large to have come from a single event. Instead, they point toward multiple supernovae, likely from the Scorpius-Centaurus group, close enough for their debris to reach our planet, but far enough to avoid causing real harm. Some researchers have speculated about whether nearby supernovae might have nudged ecological changes or pressured certain species. But these ideas remain debated, with no firm conclusions. What matters is simpler and far more comforting. Earth lived through these events. Your world has already moved through the galaxy's fireworks more than once, and it is still here, calm beneath your feet. Your oceans hold traces of ancient stellar deaths. The air you breathe contains atoms forged in stars that ended long before your ancestors walked upright. You are living on a world shaped in quiet ways by the galaxy's rarest outbursts. So, what exactly causes a star to reach that final, brilliant moment? Not all stars die the same way. Some collapse, some ignite, and the difference between the two is one of the most beautiful contrasts in the universe. One path is a giant running out of breath. The other is a quiet hoarder reaching its final limit. Two endings, two signatures, both shaping the galaxy in their own ways. The first path belongs to massive stars, those 8 to 30 times heavier than the Sun. They spend their lives burning hot and fast, fusing heavier and heavier elements in their cores. But eventually, they reach iron, a dead end in nuclear fusion. When the core can no longer support the weight above it, gravity wins. The core collapses in seconds, shrinking from the size of a world to the size of a city. That collapse unleashes a shock wave that rebounds through the star's outer layers, tearing them free at incredible speeds. What remains is a neutron star, dense enough to fit a mountain into a teaspoon. Or, if the star was truly massive, a black hole. The second path belongs to stars like the Sun. They end their lives gently, shedding layers and leaving behind a white dwarf, a dense ember that slowly cools. But in certain systems, a white dwarf has a companion. It pulls material from its partner, grain by grain, as if saving it for a moment it does not fully understand. Eventually, it reaches the Chandrasekhar limit, a mass threshold beyond which it cannot remain stable. Instead of collapsing, it ignites. Runaway fusion races through the entire star almost instantly, turning it into a cosmic flashbulb. A Type Ia supernova leaves no remnant behind, only the expanding shell of its own final blaze. Type II collapses. Type Ia ignites. One gives birth to neutron stars and black holes. The other erases itself completely, and both are essential to the galaxy. Type Ia supernovae are so predictable in their brightness that astronomers use them as cosmic distance markers, standard candles that helped reveal the accelerating expansion of the universe. Type 2 explosions, meanwhile, seed the galaxy with heavy elements, enrich star-forming clouds, and create superbubbles like the one you live in. These two paths shape everything from the metals in your blood to the structure of the Milky Way. And they show that even among endings, nature finds variety, rhythm, and meaning. So now that you understand how these fireworks happen, what happens if one goes off too close to us? Space can be dangerous on paper, but distance is an excellent safety feature. A supernova is only harmful if it erupts close enough for its radiation to overwhelm Earth's natural shields. And close in cosmic terms is far closer than most people imagine. There are 3 simple zones to keep in mind. Within 25 light years lies the true danger zone. A supernova inside this boundary could deliver a blast of ultraviolet and gamma radiation strong enough to damage the ozone layer and raise cosmic ray levels for tens of thousands of years. It would not instantly sterilize the planet, but it could pressure ecosystems. Luckily, stars that can explode like this rarely sit so close to worlds like ours. In fact, none do today. From 25 to 250 light years, the influence becomes mild. Earth might experience a dusting of debris, like the iron-60 atoms found in deep-sea sediments, or a subtle rise in cosmic rays that could nudge climate patterns. But life continues. The fossil record shows no catastrophic global collapse tied to such events. These are gentle fingerprints, not threats. Beyond 400 to 500 light years, a supernova poses no practical harm at all. At that distance, even a brilliant stellar death would be nothing more than a beautiful celestial event, something you could safely admire from the comfort of a dark field at night. Most of the stars people worry about, Betelgeuse, Antares, Rigel, are far beyond the danger zone. Many are hundreds of light years away, and even when they do explode, Earth will be untouched. You are wrapped in layers of shielding, the heliosphere pushed outward by the sun's wind, Earth's magnetosphere, and the thick, protective atmosphere above you. To threaten Earth, a supernova must be incredibly close and poorly timed. The universe is rarely that unkind. The galaxy has already thrown 2 supernovae near Earth within the last 10 million years, and your planet passed through both events unharmed. So, is there any star out there we should actually worry about? If a supernova has to be within 25 light years to be dangerous, is anything that close? It's one of the most common questions people ask when they hear about stellar explosions. The short answer is simple: no. Not a single known star within that radius is capable of going supernova. Let's look at the names that tend to worry people. Betelgeuse, for example. One of the brightest red supergiants in the sky. It's enormous, unstable, and unquestionably nearing the end of its life. Astronomers agree it will explode sometime within the next 100,000 years, maybe sooner, maybe later. But its distance, somewhere around 550 to 650 light years, places it far outside the true danger zone. When it goes, it will be a grand light show, not a threat. Antares, another red supergiant people point to, sits more than 400 light years away. It is well beyond the range where a supernova could meaningfully affect Earth. These are cosmic fireworks waiting to happen, but not aimed at us in any way. What about white dwarfs? They are fainter, harder to spot, and some type Ia supernovae come from white dwarfs in binary systems. For years, astronomers wondered whether any nearby candidates were approaching a dangerous limit. Thanks to the Gaia mission, we now have a detailed catalog of roughly 13,000 white dwarfs within a few hundred light years. None of them show the mass, the configuration, or the interaction needed to become a near-future supernova close to Earth. The science is clear. No known star within 25 light years has the potential to explode in a way that threatens our world. If the galaxy were planning a dangerous supernova for us, it forgot to put the star in the right place. You can let go of the worry. The night sky may be full of giants nearing their finales, but they are far, far away. What awaits us when they erupt is wonder, not danger. And on top of distance, we have something else on our side: layers of protection. Long before any radiation from distant stars reaches Earth, it must pass through 3 powerful shields, 3 layers that stand between you and the galaxy. Together, they form one of nature's most elegant defense systems. The first is the heliopause, the outer boundary of the bubble carved by the sun's wind. The solar wind pushes outward in all directions, creating a protective shell where incoming cosmic rays lose energy or are deflected. It is not a wall you can see, but it is a wall that works. The second layer is Earth's magnetosphere. Imagine a magnetic cocoon wrapped around your world, guiding charged particles along curved paths instead of letting them strike the atmosphere directly. This cocoon deflects most of what slips through the heliosphere and funnels the rest harmlessly toward the poles, where it becomes aurora instead of danger. The last layer is the atmosphere itself, a sky thick enough to swallow much of the ultraviolet radiation and scatter high-energy particles before they ever reach the surface. The ozone layer absorbs the harshest wavelengths, turning them into heat long before they can touch life below. Distance protects you from nearly all supernovae, but even if something bright appeared slightly closer, it would still have to cross all 3 layers of shielding. You are sitting 3 layers deep in protection, inside a bubble, inside another bubble, inside a galaxy full of patterns. You're safer than you think. The universe is big, but you're not defenseless. With that peace of mind, let's look at something purely beautiful: how we map the hidden parts of our galaxy. For decades, astronomers knew the Milky Way was hiding something from them. The thick dust in the galaxy's plane blocks visible light, turning the center of the Milky Way into a glowing blur. We could see hints of structure, but not the heart of the galaxy itself. To understand our home more clearly, scientists needed a way to peel back that dusty curtain. Enter VISTA, a powerful infrared survey telescope perched high in the Chilean Andes. Over 13 years, it captured more than 200,000 images and collected nearly 500 terabytes of data. Unlike visible light, infrared wavelengths slip between dust grains, carrying the hidden landscape behind them straight to our detectors. With VISTA, familiar regions transformed. The Lobster Nebula, which appears as a soft, misty cloud in visible light, suddenly revealed hundreds of thousands of stars in infrared. Dark patches that once looked empty became crowded fields of light. Whole regions of space that had been invisible for centuries lit up at once. The survey stretched across much of the galaxy's inner disk and bulge, covering almost 80% of the Milky Way's luminous mass. For the first time, astronomers built a detailed infrared map of the galaxy's heart, a map rich enough to trace hidden clusters, faint streams of stars, and structures no optical telescope could hope to reveal. When you switch to infrared, the galaxy suddenly looks crowded, alive, and full of secrets we almost missed. And once that curtain of dust was lifted, the Milky Way's hidden architecture began to appear. When astronomers lifted the curtain of dust with Vista's infrared eyes, they didn't just see more stars. They saw layers, histories, threads of time woven together at the Milky Way's core. What looked like a single glowing bulge in visible light turned out to be a landscape, alive, structured, and full of surprises. One of the first discoveries was unexpected youth. In a region long assumed to be populated almost entirely by ancient stars, astronomers found Cepheids, young, pulsating stars only a few tens of millions of years old. They formed a narrow, elegant structure, a thin disk of young stars cutting straight through the bulge. This was a revelation. The bulge was supposed to be old and quiet, a fossil of the galaxy's early years. Instead, here was evidence of fresh star formation, a reminder that even the galaxy's heart still draws breath. Then came something older, much older. Hidden near the very center were 12 RR Lyrae stars. These stars are ancient markers, relics of the early universe, older than most structures in the Milky Way. RR Lyrae stars almost always live in globular clusters, those dense, spherical collections of old stars orbiting the galaxy like memories. Finding them so close to the nucleus suggested that a primordial globular cluster had once wandered too near the galactic center. Over time, tidal forces shredded it, scattering its stars and leaving only faint clues behind. The bulge, it seemed, was not just a place where new stars could form. It was a graveyard for some of the oldest star clusters ever born. And the surprises didn't end there. As Vista combed through the dust, it uncovered two extremely faint globular clusters, VVV-CL0-01 and CL-CL02. One of them may be the globular cluster closest to the Milky Way's central black hole. Even stranger, the two clusters might form a gravitationally bound pair, a binary globular cluster slowly dancing around a shared center. They had remained hidden for billions of years, simply because the dust was too thick for visible light to escape. Beyond these ancient clusters, Vista unveiled 96 new open clusters. These groups of young, loosely bound stars are far more fragile than globular clusters, and they disperse over time like handfuls of glitter thrown into the air. Many of the newly discovered clusters lie on the far side of the galaxy, regions almost impossible to study before infrared surveys. They are the newest chapters in the galaxy's diary, scattered along spiral arms we could barely trace until now. Piece by piece, a richer picture emerged. The young, thin disk weaving through the bulge tells a story of recent star formation. The RR Lyrae hint at ancient star clusters torn apart in the galaxy's early years. The new globular clusters speak of hidden relics waiting just behind the dust. The open clusters reflect ongoing birth, scattered across the far side of the Milky Way. Taken together, these discoveries show that the galactic center is not a monolithic structure, but a palimpsest. Old stories written underneath new ones, each layer faintly visible through the next. At the galaxy's heart, we see both newborn stars and relics older than almost anything we know. The center of the Milky Way is alive, layered, and still in motion, carrying the fingerprints of events that stretch from the dawn of the universe to the present. And here you are, in the middle of all this structure and history, just trying to fall asleep under one small patch of that sky. Tonight, you've traveled across scales that stretch from the space just outside your doorstep to the deepest layers of the Milky Way. You've drifted through the local hot bubble, a hollow carved by 15 ancient supernovae. You've followed the shock waves that shaped young stars along its outer shell. You've seen the sun drift into the bubble long after the explosions faded. You explored how rare and gentle supernovae truly are, and why distance and layered shields keep Earth safe. Then you stepped into the infrared glow of Vista's maps and into the hidden architecture of the galaxy's core. Now, everything you've heard folds back into the same quiet truth. That something strange hiding beyond your solar system isn't a threat. It isn't a lurking danger waiting for the right moment. It is a structure, a memory, a quiet hollow that holds the story of dead stars and newborn light. A place sculpted by events long finished, wrapped around your world like a cosmic afterthought. As you lie under the night sky, whether you can see the stars from your window or just imagine them, you're resting inside this layered universe. Around you are the shields of your planet, the bubble carved by other suns, and beyond that, the swirling patterns of a galaxy that has been writing and rewriting itself for billions of years. Human lives have bubbles too. Stretches of calm after seasons of noise. Pockets of space where you relearn how to breathe, where the past no longer shakes the walls around you. The galaxy keeps its quiet hollows, and so do you. For tonight, you don't need to solve any of it. You don't have to picture every layer. You don't have to hold the galaxy together in your mind. You are allowed to rest while the universe keeps doing what it has always done. Create, destroy, recycle, and glow. You're safe. The universe is still humming softly in the background. Good night, traveler. The universe is still busy shaping itself, but for now, you can rest.